Hi, this is Dane Quinn from the University of Akron, and today I'd like to talk about kinetic and potential energy. This is for fundamentals of mechanical vibrations. So let's start off with kinetic energy. And it's usually represented with a T. It's the energy that is associated with motion. So as an object moves, how much energy is contained within that motion. So here, let's assume we have a particle P, and it has a mass m and some velocity. Right, so we'll say the velocity of P is in this direction. So in this case, the kinetic energy is 1/2 times the mass times, we often say velocity squared, but really it's the speed squared. Velocity is a vector quantity with magnitude and direction, and when we talk about kinetic energy, it's a scalar quantity. So it's really the speed squared. Well, speed is the magnitude of velocity, and the easiest way to find the speed squared is to simply dot the velocity with itself. So again, it's 1/2 times the magnitude of the velocity squared, which again is the speed. So that's kinetic energy for a particle. What about potential energy? Well, potential energy is usually given by a V, and it describes the forces that are conservative, right? Or describes conservative forces. So what makes a force conservative? Well, it's a force that's derived from a potential function. So if we had, say, a force here, right, and we'll label that F, and it's applied at a location, say there, and that location is given by a vector x, then this force can be written as minus the partial of the potential energy function with respect to x. So it's a gradient, right? It's a derivative. It's a partial derivative, really. It's a partial derivative of a potential function with respect to the displacement. So any force that can be described in this way is, again, by definition, conservative. And these kinds of forces will be very important in our application of Lagrange's equations. So let's go and look at both of these in a little more detail. And we'll start off with kinetic energy. Right, so what we just saw is that for a particle, the kinetic energy is 1/2 m speed squared, v squared. Now, we deal with rigid objects, though. So how do we go from a particle to a rigid body? An object with finite size and finite mass. Well, so let's say that body is labeled as B. So the kinetic energy of the body is basically the sum of all the kinetic energies of all the little pieces. So let me take a little bitty mass element, dm, and I'm going to actually kind of pull that out, and I'm going to look at how much kinetic energy is in this. Right? So here, this little piece has a kinetic energy of T dm. So basically, the kinetic energy of the body, I integrate over the whole thing all these little bitty bits of kinetic energy. Well, how much kinetic energy is in this small mass element dm? Well, once again, let's assume that it has a velocity, v, and we'll say it's v of dm, right? So that indicates the velocity of this little bitty mass element. So the kinetic energy can be written as the integral over the body of v dm dot v dm. So there's kind of the speed squared divided by 2, and then multiplied by this little mass element dm. And again, this also serves as the differential over the object. So really the kinetic energy of the whole body is made up of the kinetic energy of all the little pieces. And this kind of makes sense. But how do we find this quantity, right? Because each particle could have a different velocity. Well, we're going to go back and make use of some of the stuff that we had done in dynamics, right? So if we think about a point G, which is the mass center, then the position of dm with respect to G we'll write as r dm with respect to G. So then, if this is a rigid object, we can express the velocity of every point in the following way. V of dm is the velocity of G plus the angular velocity of the body cross r of dm with respect to G. Right? So again, this is the angular velocity. This is going to be very important. Right? Essentially, it's how this object spins. So now, we're going to focus on planar dynamics, and that simplifies things greatly. We really won't discuss three-dimensional motion in this course, but so for planar dynamics, so all of the motion exists in the plane. You can think about the plane of the paper or the screen here. The angular velocity is always out of the board or out of the screen, right? So it's going to be in the k direction if we assume, for example, I, j, and then k comes out of the board. And as a result, this reduces considerably. And here, what we find is that the kinetic energy of the object is 1/2 times the total mass times the speed of the mass center squared plus 1/2 times the moment of inertia of the object about the mass center times the angular velocity squared. And I'm not really going to go through the reduction here, but essentially you take this and you dot it with itself, right? So when I take these this term and dot it with itself, I get a Vg dot Vg term. I have a mixed term which actually ends up dropping out because G is the mass center. And then I have this other term which looks like omega cross r dm with respect to G dot itself. And that term, it turns out, is precisely the definition for the moment of inertia times omega squared. And so what we see is that this piece is the kinetic energy of the body due to translation. So if this object was simply translating along with no rotation, then all we would have is this term. While this last term is the kinetic energy of the body due to rotation. So if the mass center was fixed and the body was simply rotating or spinning about that, then this would be the kinetic energy. And in general, kinetic energy arises from both rotation and translation of the object. So now a little more. Here it is again. And this actually can be simplified in two important cases that we'll deal with quite often. So let's go through and discuss those. So here they are. They're pinned and rolling, right? So the kinetic energy of the body simplifies when either the object is pinned at a point O to the ground, right? So that's shown here with this bar pinned at O. Or the other case is rolling without slip again on the ground. So that's this second drawing where I have a disk that's rolling on the ground, and I assume there's no slip at the contact point C. Right, so what happens in these two cases? Well, in this case, we find that the velocity of G is the velocity of O, and again, these are kinematic equations from dynamics. R of G with respect to O. Here, the velocity of O is 0. And so, as a result, what we find is that if the distance between O and G is d, then the magnitude of V, or the speed of G, is equal to d times omega. And so when I go back up into the expression for the kinetic energy, we find that TB is 1/2 m. Now, again, this is speed squared, so that's just d omega squared plus, and then the last term stays the same, whatever the moment of inertia is, times omega squared. Well, both of these terms have an omega squared, right? So I can factor that out, and I get md squared plus ig beta omega squared. And you might recognize this. This is exactly the parallel axis theorem. So this, in fact, is I about O omega squared. Right? So again, this step going from this quantity in parentheses to here is the parallel axis theorem. So in this case, the kinetic energy reduces to 1/2 times the moment of inertia of about the pin joint times omega squared. And now, if I look at the case where we have rolling without slip, we have something similar. Vg is Vc plus the angular velocity cross r of g with respect to c. And once again, because it's rolling without slip, this term vanishes, and so that the velocity of c, its magnitude, is r omega. And just like before, we find that the kinetic energy is 1/2 times the mass, r omega squared, plus 1/2 ig omega squared. So again, exactly like before, we can factor out an omega squared. mr squared plus igb omega squared. And this is exactly the same kind of thing. It's now the moment of inertia about the contact point times omega squared. So in these two cases, the kinetic energy simplifies considerably. Once again, we use the parallel axis theorem to go from here to there, and we end up with 1/2 times the moment of inertia about either the pin joint or the contact point times omega squared. Now, I will emphasize that these only work when the point O is pinned to the ground, or it rolls without slip on the ground. That ground part is really important. ground is an inertial space. And if this was rolling on something that was accelerating, if it was pinned to a point in motion, or pinned to another object that was non-inertial, then this would no longer be possible, right? So you really have to be careful when you apply these simplifications, that you make sure that you're either pinned in the ground or you're rolling without slip on the ground. But so now let's turn to the potential energy. So again, we saw conservative forces they arise from potential functions, right, or from the potential energy. And here we have two of the most common types of conservative forces that we'll see in this class. Elastic forces, namely springs, and gravitational forces. Right, so for a spring force, and let's assume that it's linearly elastic, right? So basically we'll have an undeformed spring, and it has, say, spring constant K, and we'll ask what happens when we deform that, right? So here, now this spring stretches, right? How much does it stretch? Well, it goes from here to there, and let's assume that that stretch is delta. So we know about springs. The force due to a spring is K times the stretch, so that's delta. In this case, it'll be in the I direction. I will be along the direction of the spring. And then on the other side, this is the negative of this force, so it's minus F and minus K delta in the I direction. Right, so this is, of course, our equation for Hooke's law. The force in the elastic, linearly elastic spring is K times the stretch. So the potential energy for this spring is simply the spring 1/2 K times delta squared. So again, when we take the derivative of this with respect to, in this case, delta would be the coordinate, we get simply K delta, which is the spring force. And again, delta is the stretch. So delta would be the appropriate coordinate. It's the stretch in the spring. So that's the potential energy for a spring, right? 1/2 K delta squared. So now for gravitational force, let's do something similar, right? So now we have the force due to gravity, and it's minus mg in the j direction, right? So that's our gravitational force. And if we define the position or the height of this mass as y, and again this mass is of mass m, g is the gravitational field, then the potential energy is simply V is equal to m times g times y. And here, y is the height above the ground, or the datum. The datum is basically where we set the potential energy to be equal to 0. So here we have the potential energy due to gravitation and the potential energy due to a spring. So those are going to be the two most common forms of potential energy that we deal with in mechanical vibrations. And really, primarily, it's actually going to be the potential energy due to a spring. Right? So it's 1/2 K times the stretch in the spring. So that's a little bit more about energy, both kinetic and potential, which, as we've seen previously, is really central to the development and application of Lagrange's equations. So there's that. Thanks so much, and I'm sure we'll meet again. Bye.